Hi guys, here we are with acid base. I'm sorry I couldn't give this lecture to you in person, but I am working day shift this week, so go ahead and record this lesson for you. I don't have transcripts for this particular one because it's not something I had planned on recording ahead of time, so it's kind of a last minute change. So anyway, acid base is a three-part lesson. Part one, we'll be discussing blood pH and buffer systems and gas transport. Part two, we'll be talking about the different parameters that are included on a arterial blood gas report. And then part three is talking about the how we test, methods of analysis, how we test arterial blood gases. So, without further ado, let's go ahead and get into this. There aren't that many objectives, so I'm just going to read through them real quick. Don't let that fool you, though. For most people, I think acid base is a little bit harder to grasp, which is kind of why I had put it where it was on the schedule, so that I'd be able to give it to you in person. But yeah, it didn't work out for the first lesson. So anyway. So lesson objectives. Number one, identify the four major buffer systems. We'll be going through those individually and spending some more time on some, less time on others. Thoroughly explain how the bicarbonate buffer system treats strong acids and strong bases. Define an acid and a base, at least as it pertains to our purposes in clinical chemistry. Explain the phenomenon of dissociation as it pertains to strong acids and weak acids. Explain how buffers resist changes to pH. Describe the interrelationship between the bicarbonate and hemoglobin buffer systems. Explain how CO2 is transported in circulation. Explain Dalton's law of gases and use it to calculate the partial pressure, taking into consideration the vapor pressure of water at body temperature, which is 37 degrees. Explain how the pressure gradient for oxygen affects the affinity of hemoglobin for oxygen. Describe the chloride shift. Identify the factors that affect the oxygen dissociation curve. Explain the P50 of a normal oxygen dissociation curve and how it varies when there is a left and right shift. And identify the types and sources of volatile and non-volatile acids that contribute to the hydrogen ion concentration in the body. So, starting with the introduction, it's necessary, of course, for the body to maintain the blood pH, and it's a very narrow range that we use for blood pH. It's 7.35 to 7.45. Now that's, of course, pH, and if you remember your studying pH in chemistry, I don't know however long you had, in the past you had chemistry, but pH, the definition of pH is the negative log of the hydrogen ion concentration, and there's a key element to that definition that I want to point out, and that is that pH is logarithmic. It's not linear. Hydrogen ion concentration is linear, but pH is logarithmic. So, in reality, uh, numerically, 7.35 to 7.45 numerically is a very, very small range. But when you consider that pH is measured using a logarithmic scale, it's actually a fairly wide range, just simply because it's not linear. Anyway, we'll get into pH a little bit more later on. So the reason is, there's several reasons why it's important for the body to maintain normal blood pH. One of the critical aspects is that um, enzymes, normal enzyme function is reliant on a fairly stable pH. And, again, if you remember back from winter term, when we studied enzymes, enzymes have a really narrow range in which they function optimally, mainly 735 to 745. But the reason for that is, of course, enzymes are proteins, and proteins are subject to conformational changes like denaturing when the pH becomes either too acidic or too basic. So enzyme function, of course, is dependent on shape, and if you alter the shape of the enzyme, then you alter its function, and we all know what happens when that happens. Enzymes don't function and metabolism ceases. So not only is enzyme function affected, but there's a number of effects that can affect the cardiovascular system as well when the pH gets either too high or too low. So it's really no easy feat for the body to maintain a normal pH range. Excuse me, and that's because the body is constantly producing acids throughout the day, just due to normal metabolism. And when we talk about acids, I kind of use that term interchangeably with hydrogen ion concentration. So just kind of keep that in mind. Anytime you see hydrogen ion, it's synonymous with acid. So normal metabolism in the body generally results in producing anywhere between 15 to 20 moles of hydrogen ions every 24 hours. So that's quite a bit of acid. And of course, knowing what effect acids have on enzyme function and proteins in general, there has to be some kind of mechanism to deal with those and prevent them from having an adverse effect on the rest of the body's normal metabolic processes. So the body is capable of functioning with plasma levels anywhere between 36 to 44 nanomoles per liter of hydrogen ion. And, as it says in the slide, deviations from these levels can ultimately result in death just because of the effect that it can have on metabolism. The body maintains its pH balance with buffer systems that are largely regulated by two major organs or organ systems. You've got the lungs and you've got the kidneys. And it's imperative that you remember that for always. The two major organs in the body that have the greatest effect on maintaining acid-base balance is the lungs and the kidneys. Highlight that, underline it, circle it, never forget it. Those are the really important to remember, okay? Lungs and the kidneys. So since we've kind of started out talking about acids, it's probably worthwhile at this point to define what an acid is. And again, if you remember back from when you took inorganic chemistry or general chemistry, you may recall that there's actually several potential definitions for acids and bases. You've got Bronsted acids and bases. You got Lowry acids and bases, and to be honest, I don't even remember what those, what the definition of a Bronsted or Lowry acid is. But for our purposes, all we really care about is that an acid is a substance that can donate a hydrogen ion. Okay, so, and that's kind of implicit as, when it's placed in solution. So anything that can donate a hydrogen ion is considered an acid. And conversely, anything that can accept a hydrogen ion is classified as a base. All right. When it comes to acid-base balance in the body, we don't forget that there's bases that are present, but we tend to focus more on the acid component. All right, you'll find that as we go through the three lessons that we primarily focus on the acid component. Okay, so that's the definition of an acid: something that can donate a hydrogen ion. Now, that being said, let's take a look at an example here. Hydrochloric acid, a pretty simple compound and easy to illustrate how acids work. So if you take hydrochloric acid, or HCl, and you dissolve it in water, you place it in water, what happens is the hydrogen ions will dissociate from the chloride ions. They come apart. So you have these free hydrogen ions floating around in the water. You have these chloride ions floating around in the water. Okay, as you can see in the illustration here, the little diagram, the chloride ions are attract water molecules around them. And the hydrogen ions do to a point as well, but they're more independent. They're more free in solution. Okay, so what I want to point out here is that when you place any acid in water, you dissolve it in water, it will dissociate. The hydrogen ion or hydrogen ions, however many the acid has, they'll dissociate away from the parent molecule. All right, but in this case, a hydrochloric acid we consider a strong acid. Okay, and strong acids dissociate more completely than weak acids do. All right, and what that means simply is that when you place a strong acid in solution, the hydrogen ions will travel farther away, physically farther away from its parent molecule. Or, in this case, the hydrogen ions will travel farther away from the chloride ions. And the implication here is that with these completely dissociated hydrogen ions in solution, or hydrogen ions are the acid component, what's having an effect on the pH. A strong acid will have more of an effect on pH than a weak acid will. And that's because unlike strong acids, weak acids will only partially dissociate. So a weak acid, when you place it in water, the hydrogen ions will move. They'll move away from the parent molecule, but not very far. Okay, they stay closer than the hydrogen ions of a strong acid. Okay, and we call, for strong acids we call that complete dissociation. For weak acids we say it's partial dissociation. Okay, so that's another, that's a concept that I think is important to try to remember and understand, because it plays a really fundamental role in understanding how buffers work. All right, so if you don't understand the concept of dissociation, you need to understand it. Okay, so if you don't, we can try to discuss it. All right. So let's talk about where these acids come from, the sources of hydrogen ions in the body. We have volatile acids that are being produced in the body due to normal metabolism. We also have non-volatile acids that are being produced. But between the two, volatile acids tend to be the larger component that are being produced. So volatile acids, the primary volatile acid being produced in the body is coming from CO2 or carbon dioxide. So, just basic glycolysis, the normal metabolism of glucose in the body ultimately ends up producing CO2 in water. So carbon dioxide, being a gas, it will dissolve readily in water, and when it does, it will spontaneously combine with water to form carbonic acid. Now, carbonic acid is a weak organic acid. Not only is it a weak organic acid, but it's also a volatile or unstable organic acid. So once it forms through the combination of CO2 and water, once carbonic acid forms, it very quickly dissociates into a bicarbonate ion, or HCO3, and a hydrogen ion. Okay, so it's a simple reaction. CO2 plus water, you get H2CO3, which is carbonic acid. When that dissociates, you end up with a bicarbonate ion and a hydrogen ion. Okay, now remember that carbonic acid is a weak organic acid, and for all intents and purposes, organic acids in general are weaker acids. Okay, so weak acids, whether you know this already or not, weak acids they can serve as buffers. Okay, and in this case, this is the backbone of what we call the bicarbonate buffer system. So before I go any further, just a quick, I want to make sure everyone's on the same page. If you're not familiar with buffers, or you've forgotten what buffers are, a buffer is a substance that can help resist changes in pH. Okay, so you probably use, in some of your chemistry exercises, where large amounts of acid or base were being produced, um, you may have had to add a buffer, maybe like tris buffer, to the reactants to help keep the pH somewhat stable. Okay, so again, uh, bicarbonate ions uh, are a major component of what we call the bicarbonate buffer system. All right. So respiration results in hydrogen ions being produced and ultimately being removed by the lungs as CO2. So remember, this whole series of reactions here, CO2 plus water going to carbonic acid and then dissociating into bicarb and hydrogen ions. Every part of this reaction is reversible. Okay, so if you kind of think of this side of the equation as what's happening out in the body, the tissues of the body, as the cell, say a muscle cell, as it's metabolizing glucose, it ends up, ultimately producing CO2 and water, uh, which will combine in the bloodstream to form carbonic acid, which dissociates into bicarb and hydrogen ion. And then once the blood gets to the lungs, it goes back the other way. The hydrogen ions recombine with bicarbonate, forming carbonic acid, which will split into CO2 and water. Of course, we can breathe off the majority of the CO2. All right. There's one other thing I want to point out here, and that is the reaction between CO2 and water that forms carbonic acid. That can occur in one of two ways. It can occur spontaneously. So if you had a glass of water and a straw, and you put the straw in the water, you blew into the water, blow bubbles in the water, you're going to end up producing some carbonic acid. So it's a spontaneous reaction that can occur. But it can also be mediated by an enzyme, carbonic anhydrase. So it can either be a spontaneous reaction or it can be an enzymatic reaction. Okay. All right, so that's the major source for volatile acids in the body. We'll talk a little bit about non-volatile acids, and if the volatile acids are being produced through the activity of carbon dioxide, then not surprisingly, the non-volatile acids are derived from sources other than carbon dioxide. All right. These are often metabolic byproducts of metabolism, and often contain some degree of sulfur or phosphorus. So a couple of good examples of non-volatile acids would be lactic acid and keto acids, such as acetoacetate and beta-hydroxybutyrate. Okay, these are acids that are produced by alternate metabolic pathways than what we see with glycolysis. So, for instance, lactic acid is produced most often as a result of anaerobic respiration of glucose, and of course, that can happen in the muscle tissues when there's there's an oxygen deficit. And then, of course, the lactic acid can be transported back to the liver, where it undergoes Cori cycle and is reformed into more glucose. But it's kind of a slow process, and so if you produce a lot of lactic acid due to a large oxygen deficit, it's going to build up in the muscle tissues, and that's why it makes your muscles sore. Keto acids, such as beta-hydroxybutyrate, these are produced, and actually acetoacetate. These are organic acids that are produced by the metabolic pathway involved in metabolizing fats. So fats, of course, can be used as an alternate source of energy, and is often the case in uncontrolled diabetics. So keto acids are being produced from fat metabolism, and they build up in the blood, and because they are acids, they can have an effect on the blood pH. In either case, lactic acid or keto acids, doesn't matter. These are going to be ultimately excreted by the kidneys, so we can identify them in urine. I did this lesson quite a while ago, so I think I had a little bit too much fun with Photoshop. But the formula that I want to throw out to you guys now is my wife is shaking her head looking at the slide here. Formula I want to throw out to you here is HA going to hydrogen ion and A, or unconjugated acid. So HA together is what we call a conjugated acid. And really, a conjugated acid is the hydrogen ion or hydrogen ions when they are attached to the parent molecule and thus forming the complete acid. So like carbonic acid would be H2CO3. That's the conjugate acid, okay? Everything together, nothing has dissociated. And then on the right side of the equation, you have the dissociated hydrogen ion and what we call the conjugate base, all right? So for, again, using bicarbonate the carbonic acid as the example, on the right side of the equation, it would be a free hydrogen ion, and then the conjugate base would be HCO3. Okay, and notice the arrows arrows going in both ways. It can go right or to the right or to the left. That's important to remember as well, because in any system, chemicals, and especially chemical systems, everything is striving towards equilibrium. Okay, so if you place an acid, in water, some of it's going to dissociate, some of it will stay associated until you have an equilibrium between the associated and dissociated forms of the acid. All right, that will be, if you can try to hang on to that concept, that'll become important when we start talking about pH and different acids, because it's a kind of a fundamental concept to understanding what is called the pKa of an acid. Okay, but I'm getting ahead of myself a little bit. So we'll let that lie for now. All right. So going kind of taking the concept in that last slide, the equilibrium between conjugated and dissociated forms of an acid, kind of take that a step further, and we can express an acid in this form as well. Okay, so we have what we call the conjugate base over the conjugate pair. Okay, so again, if we stick with the carbonic acid example, the conjugate base would be HCO3, or bicarbonate, a bicarbonate ion, and the conjugate pair would be H2CO3, or carbonic acid. All right, and that's true for any acid. Okay, you can express it as the conjugate base over the conjugate pair. All right. So where I'm heading with this is we're going to be talking about buffers, because if you remember a few slides back, the body's producing a lot of acid on a daily basis just because of through normal metabolism, and the body has to have a way of dealing with all of that acid being produced. So that occurs mainly through the interaction of those acids with buffers in the body. Okay, so conjugate base over the conjugate pair is how we generally express these buffers. And if you want to use the example from the previous slide, we can just plug that into the same formula. So you'd have the dissociated hydrogen and the conjugate base over the conjugate pair. Okay. Okay. So this next slide, I want to introduce the most important buffer systems in the body. Okay, and essentially it looks like there's 6 of them here, but I kind of combined a couple of them and say that there's 5. Okay, 5, 6, depending on how you look at it. But the buffer systems can be divided between what happens inside of a cell and what happens outside of the cells. Okay, so we have the intracellular fluids, or the ICFs, and we have the extracellular fluids, or the ECFs. Okay, we'll start with the intracellular fluids because they're important, but they're generally not as important in controlling blood pH as the ones in the extracellular fluids. So we've got what's called the phosphate buffer system. I'll go through that briefly in the next few slides. So there's one. We have the hemoglobin buffer system, which by definition is only in the red blood cells. So hemoglobin buffer system, that's another one of the 5. Then we have the protein buffer system, and this is kind of where if you want to get detailed, you can separate them out into the different proteins and where they're found. For our purposes, I just I lump them all together and say, hey, you've got the protein buffer system. So that would include amino acids, which are a part of all proteins, and sometimes some of those are going to be found in the intracellular fluids, but then you also have the plasma proteins, which of course are in the extracellular fluids. So that's another one. And then I have this circled, this next one circled, because it is the single most important buffer system in the body. And that's the carbonic acid bicarbonate buffer system. Okay, without it, we couldn't live. Life wouldn't be possible. So we'll be focusing primarily on this one buffer system. All right. Okay, so let's start with the number one most important buffer system, and we'll go through this in a lot more detail than we will the other four. Okay, so remembering that we express buffers as the conjugate base over the conjugate pair. Here it is. Bicarbonate. Here I have sodium bicarbonate, which is fine. That's how bicarbonate ions are stored in the body. So you can think of the conjugate base as either sodium bicarbonate or just bicarbonate over the conjugate pair, which is carbonic acid. All right. So the conjugate base, like I just mentioned, bicarb and sodium bicarb. The only real difference between these two is the sodium bicarbonate is how we store excess bicarbonate in the body, and then the conjugate pair being carbonic acid, of course. So this particular diagram kind of gives you a little bit of an idea, kind of a basic idea of how the bicarbonate buffer system works. Okay, so if we start up here, we look at the top. Over on the right side, we have the bicarbonate reserve, remembering that sodium bicarbonate is how the body normally stores excess bicarb. And then on the left, we have how, what's happening with the bicarbonate buffer system, how it deals with excess hydrogen ions. Okay, so these hydrogen ions, we're going to say these hydrogen ions are coming from normal metabolism of glucose. As hydrogen ion concentration begins to increase in the blood, bicarbonate ions that are also free in the blood, they can combine with those free hydrogen ions, forming carbonic acid, which, under the influence of carbonic anhydrase, that can split into CO2 and water, and we breathe that off in the lungs. Okay. If we don't have enough hydrogen ions in circulation, then the body can conserve, our breathing, our respiratory rate decreases, so we conserve more CO2, which means we're making more carbonic acid, which can be split into bicarb and hydrogen ions. So this is a completely reversible process, depending on whether we have too much hydrogen or not enough. Okay. And the same can be said for fixed acids or organic acids. The same thing is happening. Okay, the excess hydrogen ions can be picked up by bicarbonate ions, forming carbonic acid, which can be split into CO2 and water and breathed off. All right. Okay, so just to take this an extra step, because of course, like I mentioned, the bicarbonate system is the most important. So I want to make sure that that everyone understands this thoroughly. All right. Let me give you an example of how the bicarbonate buffer system works when we have a strong acid and when we have a strong base. Okay. And I'm not much into memorizing chemical reactions, but this is one I want you to know. I guarantee you this will be on the exam. Okay, so you need to be able to recognize this and understand what's happening in each of these reactions. Okay, so let's start with a strong acid. So we have the bicarbonate buffer system here, right? Sodium bicarbonate being our conjugate base, and then carbonic acid being the conjugate pair. And that's true in both cases here, all right? But in this instance, we're adding a strong acid, hydrochloric acid. Now, with this buffer system, when we add a strong acid, it's going to react with the conjugate base. Okay, strong acid is going to react with the conjugate base, whereas a strong base will react with the conjugate pair. All right, so kind of keep that in mind. So coming back here with hydrochloric acid will react with the sodium bicarbonate in the solution to form 2 molecules of carbonic acid and 1 molecule of salt. Okay, so sodium chloride, of course we know that is salt, but in reality sodium chloride is the salt of hydrochloric acid. Okay, pretty much all acids will have their own salt, okay, depending on the metal that they combine with. But in this case, the salt of hydrochloric acid is sodium chloride. That's not as important as this this product here, 2 molecules of carbonic acid. So remember, earlier I told you carbonic acid is a weak organic acid, right? And I also told you that hydrochloric acid is a strong acid. So look what we've done here by using this particular buffer system. Hydrochloric acid reacts with the conjugate base to form carbonic acid. We've just converted or transformed a very strong acid into a weaker acid. And this is exactly how buffers work. Buffers resist changes in pH by converting a strong acid to a weaker acid. Okay, so that's really the basis of how buffers work. All right, now that's a strong acid. Let's take a look at what happens with a strong base. In this case, sodium hydroxide. Okay, when we add sodium hydroxide to the same buffer system, rather than reacting with the conjugate base, sodium hydroxide will react with carbonic acid, the conjugate pair, which is essentially is the acid part of this buffer system. Okay, so sodium hydroxide, a strong base, is going to react with the conjugate pair or carbonic acid, and we end up with 2 molecules of sodium sodium bicarbonate and water. All right, so sodium bicarbonate, that's our conjugate base, right? So we've converted or transformed a strong base to a weaker base. All right, it's also worth pointing out that if you look at both of these reactions, hydrochloric acid, when it reacts with the conjugate base, it ends up not only producing a weaker acid, but it's the same acid in the buffer system that is present. Okay, so we're converting a strong acid to not only a weak acid, but it's the conjugate pair for the buffer system, right? And in this reaction here with the strong base, the strong base is reacting with the conjugate pair, and the product is the conjugate base. All right, so it helps to feed the same buffer system that's working on these strong acids and bases. Okay. Again, I want you to know these reactions, be able to regurgitate them, because I guarantee you'll see questions related to this on the exam. Okay, so the bicarbonate system is unique when compared to the other buffer systems. Primarily because it has a huge buffering capacity throughout the body. The body makes lots of carbon dioxide. We have lots of water, not only in the tissues but also in circulation. So it's possible to make large quantities of carbonic acid and bicarbonate ion. It's also an open system, meaning that it interacts with the air as well as the tissues of the body. All right. So because of those things, it has a huge capacity. All right. All of the other buffer systems in the body, the protein buffer systems, the phosphate buffer system, the hemoglobin buffer system, all of those are what are considered a closed system. They don't interact with the air, so they don't have quite as large of a buffering capacity as the bicarbonate buffer system does. All right, next up is the phosphate buffer system, and I'm not going to spend very much time on this at all because it doesn't play as large of a role in maintaining the blood pH. It's important, of course, in the cells, but we're not really interested in generally what's happening in the cells. We're more focused on what's happening in circulation. But regardless, the phosphate buffer system starts out with H3PO4, which can dissociate. There's 3 hydrogens here, right? One of those can dissociate, so you have a free hydrogen ion and H2PO4, and that can still dissociate, so that you have 2 free hydrogen ions and HPO4, and of course you can lose the 3rd hydrogen ion as well, so you end up with just a phosphate group, PO4. Okay, the conjugate base is HPO4, and the conjugate pair is H3PO4. All right, so it has a good buffering capacity because of the number of hydrogen ions associated with it, but there's very little of this in circulation. It's primarily in the tissues. Proteins, on the other hand, are found both intracellular and extracellular. So we got, of course, plasma proteins, namely albumin, along with a number of globular proteins. And if you're wondering how do proteins serve as a buffer, think of it this way. If you've ever had acid indigestion or heartburn before, and if you drink a glass of milk, it tends to have a very quick effect on on the symptoms. You know, your heartburn symptoms tend to, if they don't completely go away, they lessen in severity. Now, granted, it usually comes back at some point. You know, it's not a permanent fix, but it does have a rather immediate effect on those symptoms. And the reason is, you know, milk is high in protein. So how do proteins function as a buffer? Well, in reality, proteins are themselves weak acids. Think about it. You know, consider an amino acid, and you know, what are the functional groups that compose an amino acid? You have alpha carbon, you have a hydrogen attached to that. You have an R group, which is, you know, is the definition of what the specific amino acid is. But then you also have an amine group, or NH3, and a carboxylic acid group, and that's the bingo. That's the functional group that makes a protein able to function as a buffer, is the carboxylic acid. So that would be C double bond O with an OH. Okay, that hydrogen ion associated with carboxylic acid, that can partially dissociate from its hydrogen. So being that it can partially dissociate, it's able to pick up another hydrogen ion, and thus that's how it works as a buffer. Okay, so any of the proteins work. They work the same way in the context of a buffer. Okay, so you get plasma proteins, namely albumin, and then you got hemoglobin. And when it comes to hemoglobin, there's two different forms of hemoglobin that we need to consider. One is oxyhemoglobin, and one is reduced hemoglobin. Now, you know, if you remember your redox reactions, your reduction oxidation reactions, anything that's reduced, that means that it has a hydrogen ion attached to it, or an additional hydrogen ion. Okay. So reduced hemoglobin has a hydrogen ion attached to it, whereas oxyhemoglobin does not. Okay. Now, having said that, and knowing that buffers, by definition, should be able to accept additional hydrogen ions, right? Which would you think would be the better buffer? The one that would more likely be able to accept an additional hydrogen ion more readily? Oxyhemoglobin or reduced hemoglobin? I'll give you a second to think about that. Okay, seconds up. The answer is oxyhemoglobin, and that's simply because reduced hemoglobin already has a hydrogen ion associated with it. So the likelihood of it being able to accept another hydrogen ion on top of the one that is already attached is lower than for oxyhemoglobin, which doesn't have any hydrogen ions attached to it. Okay. All right. So this table here is just a summary of the buffers that we just discussed. Okay, you got the bicarbonate buffer system, the plasma protein, phosphate, and hemoglobin. Okay, so the acid component, of course, from the bicarbonate buffer system is carbonic acid. The base component is bicarbonate, and its functions primarily in the extracellular fluids. For plasma proteins, the acid component is reduced carboxylic acid, So you got the protein with a reduced carboxylic acid group. The base component would be the partially dissociated carboxylic acid group, and again, it's plasma proteins, not all the proteins. So of course, this is extracellular fluids. Phosphate group, you've got H3PO4, which is technically orthophosphoric acid. The base component is HPO4, which is metaphosphoric acid, and for God's sake, you don't have to remember the names of these. It's just for inquiring minds that want to know. And like I mentioned before, this phosphate group or phosphate buffer system functions primarily intracellularly. And then the last, we have hemoglobin. So acid component is reduced hemoglobin, base component is oxyhemoglobin, and unless you talk about hemolysis, this should function primarily in the intracellular fluids. Okay, so hopefully this is making sense, at least up to this point. Okay, so let's try to put this into practice. Let's consider the practical application of specifically the bicarbonate and hemoglobin buffer systems. All right, so kind of looks like a little maze here. We're going to start over here on the bottom right side. This would be out in the tissues of the body. Okay, so this is where we're going to start. And as we know, normal metabolism of glucose is going to result in production of carbon dioxide and water. Okay, so when carbon dioxide diffuses across, out of the cell, it's going to come into contact with water in the plasma or water in the red blood cells. In any case, let's stick with the red blood cells. Okay, that is going to make this easier to understand. So CO2 crosses from the tissues of the body into the red blood cell, and of course there's water in the red blood cells, so it's going to combine with water to form carbonic acid. Now we know carbonic acid is pretty volatile, it's unstable, so it very quickly dissociates into bicarb and a hydrogen ion. Now, when that occurs, the bicarb leaves the red blood cells and goes out into just the plasma. Okay. The hydrogen ion, however, does not, and as hydrogen ions build up inside the red blood cell, they actually help to kick off oxygen. Okay, so if you have oxyhemoglobin in the red blood cell, hydrogen ions are one of the factors that help release oxygen from hemoglobin so that it can cross over to the tissues, peripheral cells. So when that happens, hemoglobin displaces oxygen. So now we have reduced hemoglobin. Okay, and that's now we're in the venous circulation. And when those red blood cells get back to the lungs, oxygen, a lot of oxygen comes into the lungs and helps to displace the hydrogen ion so that the hemoglobin is now oxyhemoglobin. But now we have this free hydrogen ion. So what happens is bicarbonate ions come back into the red blood cell. They recombine with the hydrogen to form carbonic acid, which is split into CO2 and water, and that is exhaled. Okay, kind of a complex process, but if you look at it in chunks, look at it in sections, you know, like this section here, and then this section here, and then this, and this, and this. Look at it in chunks. It's a little easier to understand what's happening at each step. This is actually, this illustration here comes out of your textbook, and this is how the majority of carbon dioxide is transported in the body. It's not transported as, you know, CO2 in the red blood cells. It's transported piecemeal as bicarbonate ions and hydrogen ions, and then just it reforms to carbonic acid and then splits into CO2 and water once it reaches the lungs. So again, this is the major way in which CO2 is transported in the blood. Okay, let's shift gears for a little bit here and talk about numbers, everyone's favorite. So we're going to discuss how gas is transported in the blood, since I kind of gave you a little introduction to that in the last slide. We're going to start off by reviewing gas pressure. So again, there shouldn't be anything new in this information. It should be stuff that you've learned previously. I'm just having to recall what you've learned before. So there's several gas laws that you probably learned about, but the one that we care about primarily in clinical chemistry is Dalton's law of gases. And it's not a complicated law, it's very simple. Dalton's law is just an expression of the total gas pressure. So if you have several gases present in the environment or in a container, each individual gas will exert a certain amount of pressure. And if you add all of those pressures up, you have the total pressure, or the sum of what are called partial pressures. All right, let's take a look at that. Normal air, atmospheric air that we breathe, is composed of oxygen, carbon dioxide, nitrogen, and a handful of inert gases. All right. And they're all present in different concentrations. So for instance, we know that the concentration of oxygen is in air is about 20.93%, or just say 21%. Okay. The normal amount of CO2 in air is 0.03%. And nitrogen is about 78.1%. And then if you take all of the weird miscellaneous inert gases, that's going to take up the remaining 1% or so. Okay, add all of these up, and you should end up with 100%. Okay, each one of these exerts pressure, its own pressure in air. So the individual pressure from each of these gases is called a partial pressure. Okay? All right. So let's take a practical example of how to look at partial pressures. And we'll start by asking, what is the partial pressure of oxygen, or PO2, we just say PO2, P for partial. What is the PO2 of 1 atmosphere at sea level? Now, remember, again, there are different units of measurement for pressure. In this particular question, we're using atmospheres. Okay. Well, we could be using torr or PSI, pressure per square inch, but in this case, we're just saying atmospheres. All right. Now, in order to determine what the PO2 of 1 atmosphere at sea level is, and this isn't just fluff. Saying that it's at sea level is important. In order to calculate the PO2, not just for oxygen, but for any gas, you need to know what the vapor pressure of water is at the temperature that you're measuring it. Okay, so for general chemistry, it's kind of a pain because the temperature can be anything. You're going to have to measure the temperature every time you're determining what the partial pressure of the gases that you're measuring. Not so for clinical chemistry, because we're really only, body temperature is considered 37 degrees, and that's the temperature that we're interested in. So, hallelujah, for us, at least we have something going for us here. We only have to remember one number. Okay, so the vapor pressure of water at 37 degrees is 47 millimeters of mercury. Okay, so that's important to remember. You need to commit that to memory. Vapor pressure of water at 37 degrees is 47 millimeters of mercury. So in order to calculate the partial pressure of oxygen in 1 atmosphere at sea level, first what we need to do is take the barometric pressure of 1 atmosphere, which is equivalent to 760 millimeters of mercury, and we subtract the vapor pressure of water. You always have to do that. That's the first step. Whatever your barometric pressure is, first start by subtracting the vapor pressure of water, which for our purposes will always be 47. Okay? So 760 minus 47, and then multiply that by the concentration of the gas. Now we know that room air contains is 20.93% oxygen. So barometric pressure minus 47 times 20.93%, that will give you, plug those numbers into your calculator, you should get the same number, 149. Okay, so that's the PO2 at 1 atmosphere at sea level is 149 millimeters of mercury. Okay. I do have some practice problems using, for calculating gas pressures. They're already posted. If you haven't downloaded them yet, it'd be worthwhile to download them and just work through a few. It's not a complicated calculation, but it's just a matter of memorizing it. Okay? Okay, next up is oxygen transport. Okay, so adult hemoglobin is hemoglobin A1, and it's good to keep that in mind because, of course, if you remember from hematology, there are a number of abnormal hemoglobin pigments that will affect oxygen transport in the body. You've got methemoglobin, you've got hemoglobin S, hemoglobin C, on and on and on. I'm not going to go through them all, but we're just going to be considering normal circumstances, adult hemoglobin or hemoglobin A1. Okay. So before we get into how how oxygen is transported and what happens with pH and oxygen transport, I want to go through the major factors that will affect hemoglobin's affinity for oxygen. Okay, so number one is the availability of oxygen. Okay, and we'll in this next slide, I've got a great diagram to kind of help illustrate that. Availability of oxygen expressed as the PO2, partial pressure of oxygen. Okay, and that's both inside and outside of the red blood cells. Okay? Also, the presence and amount of any abnormal hemoglobin pigments. All right, pH, PCO2, and 2,3-DPG, okay, or 2,3-diphosphoglycerate. You may hear it referred to as 2,3-bisphosphoglycerate, the same thing. Okay, and then the transference pressure of oxygen, which is anything less than 60 millimeters of mercury. So what this is referring to is when it comes to oxygen transport in the blood, oxygen will want to go towards a pressure less than 60 millimeters of mercury. Okay, so if the bloodstream has a oxygen pressure of less than 60 millimeters of mercury, that's where oxygen is going to want to go. Okay. All right, so let's take a look at this. Actually, two different diagrams. If you draw a line, imaginary line down the center of the slide, the left part is what's happening in the lungs, and the right half is what's happening out in the peripheral tissues. Okay, so let's start with the lungs. Okay, we'll start with venous blood. So venous blood is going to be pumped from the heart into the lungs, and generally, the general PCO2 and PO2 of venous blood is 45 and 40 respectively. Okay, so a PCO2 of 45 is normal for venous, and a PO2 of 40 is normal for venous. Okay, now out here in the atmosphere that's being, we're breathing, the PO2 is 160 millimeters of mercury. Okay, the PO2 of venous blood is 40. 40 is less than 60. So that's going to be a major factor that will help oxygen, direct oxygen into the red blood cells. Okay, so you're breathing air with a PO2 of 160, and when it gets down into the alveolar sacs, PO2 actually drops down to about 105 because it's being absorbed by cells and fluid as it's making its way down to the alveolar sac. So some of the PO2 is being dissolved in fluids like lung fluids, tissue fluids. So it decreases to about 105. And so again, 40 is less than 60, 105 is greater than 60, so oxygen is going to want to move from the alveolar sacs into the blood cells. When that happens, then the blood becomes arterialized, and the PO2 goes from 40 to about 100, 105. Okay. And the PCO2 goes from 45 to 40. Now that is a significant relationship that is very important for you to see, to recognize. The fact that the PO2 from venous blood changes so dramatically, 40 to 105, that's fine. The fact that PO2 just itself, the fact that PO2 is changing back and forth between 40 and 105 won't have any effect on the blood pH. Now, it will indirectly because of the effect it has on the peripheral cells, but the gas itself, all other things being equal, the fact that we're changing back and forth between 40 and 105 doesn't have any effect on blood pH. All right? Look at PCO2 though. PCO2 of venous blood is about 45. For arterial blood, it's about 40. That's a very little difference. That's a very small difference between venous and arterial blood. The reason that is so important is because CO2 is so critical for producing carbonic acid. And of course, carbonic acid does have an effect on blood pH. So if you had the same large numerical changes between PCO2 that we see with PO2, we would have really large swings in pH between venous and arterial blood, which really isn't compatible with life. All right? So that's an important relationship to be able to recognize. Now let's take a look at what happens when blood reaches the peripheral tissues. This arterialized blood that makes its way into the capillaries, again, has, just like we saw over here, has a PO2 of about 105 and a PCO2 of 40. And then in the peripheral tissues, the PO2 is low. It's about 40. The PCO2 is about 45. So because the PCO2 is so low, it's lower than 60 in the peripheral tissues, oxygen is going to want to leave the red cells in preference of the peripheral tissues. Okay. At the same time, CO2 diffuses across the membrane and is picked up by the red blood cells. So that's the basic circulation of oxygen and CO2 between arterial and venous circulation. Now, what I have failed to mention here, and we'll see in the next slide, is there's more than just the partial pressure of oxygen that's affecting where oxygen is being directed, whether to hemoglobin or to the peripheral tissues. There's a number of other factors that we mentioned in the last slide, and we're going to take a look at those and see how they affect the oxygen dissociation curve. So, you probably learned about the oxygen dissociation curve in hematology. You're going to get it again because it's such a fun concept to learn. So we're going to start with introducing a concept that I don't know if you learned about in heme or not, and that is something called the P50. So, what the P50 is when hemoglobin is 50% saturated with oxygen. The PO2 should be somewhere between 26 and 27 millimeters of mercury. So if we look down here on the x-axis, we have partial pressure of oxygen, And then on the y-axis, we have hemoglobin saturation. Okay, so here's 50% saturation on the y-axis. We draw a straight line over until it intersects our curve. Don't worry about the dotted lines yet. Just look at the middle solid line is the normal curve. Okay, so where it intersects the curve, we draw a straight line down, and voila, a normal oxygen dissociation curve shows that when hemoglobin is 50% saturated, the PO2 is, what do you know, 25 or 26, 27 millimeters of mercury. Okay, you can also look at this in kind of the opposite direction. So, for instance, rather than saying when hemoglobin is 50% saturated, the PO2 is 26 to 27, you could also say that when the PO2 is 26 to 27, hemoglobin should be 50% saturated. All right. I always kind of think that, at least for me, that's kind of an easier way of looking at it, or it makes more sense to me by looking at the pressure and then associating that with the percent saturation. Now, on either side of this normal curve, you have dotted lines, which represent the abnormal curves. So the abnormal curve on the left is a shift to the left, and what that means is there's a decreased affinity for oxygen. Hemoglobin has a decreased affinity for oxygen. It doesn't want to hang on to oxygen very much at all. Okay, so let's take a look at that in our next slide. So a left shift as it pertains to the dissociation curve is simply, when the oxygen saturation is greater than 50%, the PO2 will be around 26. Okay, or when the PO2 is 26, hemoglobin will be more than 50% saturated. So if you take a look here, here's, let's say, if this is 30, it's right in between 20 and 40, right here. 26 to 27 would be about here, and we draw a straight line up as best we can, and it's somewhere around here, right? And we draw a line over, and what do you know? Our hemoglobin saturation or oxygen saturation is, I don't know, that looks to be about 75%. Okay? So, the factors that can cause this are increased pH or alkalosis, okay, decreased PCO2, a decreased 2,3-DPG, and a decreased temperature. All right, so let's take a look at each one of these and kind of figure out why do each of these, what effect is it having? Why does it cause this increased affinity? Start with alkalosis. Okay, and actually, you could take a look at both increased pH and decreased PCO2. They actually go hand in hand. They are directly related to each other. Because remember, PCO2, when it combines with water, forms carbonic acid, right? Acid. So if you don't have enough PCO2, less than you normally should, that will lead to alkalosis because you're producing less acid. So the reason that alkalosis will cause increased affinity of hemoglobin for oxygen is, remember, one of the factors that helps to hemoglobin to release oxygen is the hydrogen ions that are produced from carbonic acid. So if you recall back when we were discussing how CO2 is transported in blood, when hydrogen ions are hydrogen ion concentration builds up in the red blood cells, the hydrogen ions displace the oxygen, causing it to release from hemoglobin. Well, if you don't have enough, then oxygen just simply stays attached to, it's more likely to stay attached to hemoglobin. Okay? Decreased 2,3-DPG. The main role of 2,3-DPG in the red blood cells is to kick oxygen off of hemoglobin. So if you don't have enough of it, then oxygen is more likely going to stay attached to hemoglobin. Decreased temperature because of decreased metabolic rate and increased solubility of gas in the blood. Okay, so these are all factors that cause hemoglobin have an increased affinity for oxygen. Now we'll look at the shift to the right. It's going to be just the opposite for the same reasons. Okay, so a shift to the right occurs when you look at the PO2 when it's 26, oxygen is less than 50% saturated. Okay, so again, we come over here. Here's 30. That's about 27. Draw a straight line up. Boom. Here's our abnormal right shifted curve. Draw a straight line over, and that's about 30-35%. Okay, so shift to the right means that hemoglobin has a decreased affinity for oxygen. It's not going to hang on to it for very long at all. Okay, and look at all these. It's the same variables, same influential factors, just the opposite on the opposite spectrum. Okay, so a decreased pH or acidosis, along with increased PCO2, there's a lot of hydrogen ions present. They're going to want to constantly kick oxygen off of hemoglobin, keeping it from becoming very saturated. A lot of 2,3-DPG, again, is going to likely kick off oxygen and keep it from becoming saturated. And then increased temperature, increased metabolic rate, equaling increased PCO2 production. Okay. All right, last concept, and then we will call it a night here. We talked about oxygen. Now I want to talk about CO2. And now I mentioned CO2 transport several slides ago, but there's a few. I want to go into a little bit more detail on what's happening with CO2 as it leaves the peripheral tissues and enters circulation. So there's really three primary forms that carbon dioxide can be transported as. We got bicarbonate ions, which is the number one most common way or form of CO2 transport. Then we have carbonic acid, which is only 1/20th of how much bicarb is being produced or transported. And lastly, we have something called carbaminohemoglobin, and this is when CO2 binds directly with hemoglobin. So this is the least common way in which hemoglobin or CO2 is transported. Okay. Now, because of these first two here, bicarbonate and carbonic acid, and primarily bicarbonate, we have something called the chloride shift, which sounds like an old dance move, but it's what happens inside the red blood cells to help balance charges. Okay, so let's take a look. So the last two slides are very similar. They're just opposite of each other. Okay, so this is what happens. We're starting out here in the peripheral tissues. CO2 from respiration is diffusing across, out of the tissue cells and into the capillaries. And the size of the arrows is indicative of how much of that particular process is going on. Okay, so the smallest arrow here is CO2 combining with water in the plasma and spontaneously forming carbonic acid, which dissociates into bicarbonate hydrogen ion. Okay, that is the least likely scenario to happen. What's more likely to occur is the big black arrow indicating CO2 entering the red blood cell, again combining with water, but in this case it's being enzymatically converted to carbonic acid through the activity of carbonic anhydrase. Okay. So the carbonic acid that's produced immediately dissociates into bicarbonate and a hydrogen ion. So the bicarbonate really doesn't do much good inside the red blood cell. It's needed outside of the red blood cell where it can pick up additional hydrogen ions. So a lot of the bicarbonate inside the red blood cell is exchanged for chloride ions. That's an important concept to understand and to remember. The fact that we are conserving charges. Okay, anytime an ion is leaving one tissue compartment for another, we have to balance the charges. So if we're kicking out a negatively charged ion, we have to swap it with another negative ion so that we have the same number of charges inside and outside the cell. Okay, so swapping bicarb for chloride, that's the chloride shift. Nothing really complicated about that. Okay, chloride really doesn't do much inside the red blood cell. It just helps to balance the charge, right? So let's move on to the hydrogen ion. The hydrogen ion that came from the dissociation of carbonic acid, that will bind with hemoglobin to form reduced hemoglobin. Okay. Another process that can occur is CO2 combining with hemoglobin to form carbamina hemoglobin. Okay. All right. Now, at the same time, oxygen is being released from hemoglobin and diffusing out of the red cell and into the peripheral tissues. Okay. Then, of course, once we get to the lungs, the opposite occurs. So bicarb enters the red blood cell and chloride is pumped out. That's the reverse chloride shift. At the same time, oxygen is diffusing into the red blood cell and kicks off the hydrogen ion. So the free hydrogen ions can combine with the bicarb and then form carbonic acid, which is enzymatically converted to CO2 and water, and then that is breathed off. Okay. So that's the chloride shift and the reverse chloride shift. Of course, you have the other processes occurring at the same time, but we're just kind of we're primarily focused on that chloride shift. All right, guys. So that is it for the first lesson. Primarily, I really wanted to make sure that you guys understood how the buffer, how buffers work, how the bicarb buffer system works, and how gases are transported in circulation. So again, there's practice problems for gas problems. They're very simple calculations to perform, but it's just a matter of practice. Okay? You need to be able to do those calculations. All right, that's it for tonight. Wish I could have given this to you in person, but this will be my last week on days, so I will see you guys next week. Okay. Have a great week, and we'll talk to you later.